So I've been doing this data science thing for like a couple of years. And what I kind of want to do is explain how I got this role at Raza and also some of the stuff I learned over the last couple of years. Because I think maybe if you're optimizing for accuracy, you're actually doing it wrong. And I kind of want to explain why, because it seems counterintuitive. But I think it's something we should talk about. Also, this will be a presentation with lots of references to Pokemon. So a little bit about me. I've got this blog called Koning.io. You might have heard from me from that. I have also been organizing PyData Amsterdam. You might have heard from me about that. I'm also the YouTuber for the Spacey project, sort of. Video just went live yesterday, so you might have heard about me about that. I have a couple of open source projects that I started. You might have heard about that. And there's some other projects that I start on the side. You might have heard about that. And recently, I started working at Raza, and you might have heard about that. I'm kind of this open source community guy. It's kind of what I do. It's what I intend on doing. It's kind of my jib. But I got here, and the story was like 8 years old now. So imagine 8 years ago, I graduated with a degree in operations research. And I taught myself how to code, and I was part of that first batch of that first MOOC. Sebastian Thrun, Andrew Oon, Peter Norvig, that first thing was a part of it. And that made me consider, I really got to do this programming thing. Is this one on, or is this one on? All right. So what happened was I taught calculus at a university. Noise. For about half a year, and then the other half a year I would travel, and what I did was I called myself an independent contractor back in the day when no one called themselves a data scientist. And something I found out was you can actually do most of that work remotely. So I did, and life was actually pretty good as long as there was Wi-Fi. It was also around that time that I became sort of an internet meme. I started sending this photo around, and people sort of noticed, and then you start trending on Reddit a bit. And then I figured, I should start this blog, because at some point, you're done with world travel, you're sort of settling down, and I wanted to sort of figure out what this data science thing was going to be. Because 6 years ago, data science was super new, so I figured whenever there's something non-obvious, I should write about that, and that should go to the blog. And then I went to this big data conference in London, Strata. And then, this was kind of my first time at a big data conference. It was also like literally a big conference. And I met this guy. And he, guy in a suit, kind of nerdy, but he wouldn't shut up about it. He kept on bragging about how he calculated the optimal portfolio of bonds using big data. And the guy wouldn't shut up about it. So I thought it was going to be funny if I wrote a blog post that was going to calculate the optimal portfolio of Pokemon, just sort of as a joke. I figured it might be funny. So, you kind of research what is Pokemon. I've never played it, but it sounds like something that's funny to check. Turns out it's this video game where you select a couple of animals and they battle some other animals. So I figured, okay, let's try to find the best Pokemon. Around that time, and I'm not joking, there was actually a research paper called Classic Nintendo Games Are Computationally Hard. I think this was Cambridge, I'm not exactly sure, but it was like an actual fundamental 10-page proof that Pokemon is NP hard, just like Zelda, Mario Brothers, and Super Mario World, and Donkey Kong. So I knew I was solving a hard problem. But the funny thing here is that there were actually these fan websites. And these fan websites, there were people who were really enthusiastic about the game. So they had all of these formulas that would explain if you have one Pokemon and it deals damage to the other Pokemon, how much damage does it do? And it depends if they're like a fire Pokemon or a water Pokemon, or I still don't know what Pokemon is, but I found the formula. And then there was also this other website, which was the Poke API. You can download any statistics you want from Pokemon. And again, here, this is the interesting thing. I have no domain knowledge about Pokemon, but I do have data, right? So the game that I'm playing here is this going to give me a competitive edge, nonetheless? So the first thing I did was I did what a BI person would do, because if you're doing stuff with data back in those days, you would sort of do the business intelligence thing, which usually means that you're making a giant visualization. So what you're looking at here is a matrix where all the Pokemon are listed, and they're battling it out against another Pokemon. So this is the result of the simulation. It's a 150 by 150 matrix, and you should see something symmetrical here. So there's this red line at the bottom here. That's Magikarp. Magikarp loses against everyone, and everyone wins against Magikarp. And the same thing with Diglett. So using BI, you quickly find out that Diglett and Magikarp are the worst Pokemon to have, which is great, but it's not what you're interested in. You want to find the best combination of Pokemon. So this is one of the moments where BI has its limits. And if you have a good BI tool, then what you can do is you can click a button and the fancy thing happens where all the Pokemon are clustered together. So you can see that all the fire Pokemon are weak against the water Pokemon, and all the grass Pokemon are weak against the fire Pokemon, etc. But this is, like, I think 7 years ago, this is what people did with data. This was BI, right? This is what they did. So I then figured, let's do kind of a data science thing with this. What I can do is I can look at an array of all of these numbers, right? And sort of say, hey, that's kind of like a time series. That's kind of like a bond. Because if you think about it, if one row here is super green most of the time, hey, that's good. That's like a bond. That's a return on the investment of a Pokemon. But if the variance is super high, that's a bad thing. That's risk. So I figured, hey, we can do math here. I can calculate the average, and I can calculate the standard deviation. These two formulas. And what you can then do is you can plot all the Pokemon where the expected return is listed on the y-axis and the variance or the risk is listed on the x-axis. Then you can sort of say, okay, let's just select these couple of Pokemon. I'm using a little bit of math and a little bit of data to figure out, hey, which Pokemon might be best. Which are these 5 Pokemon. I later found out that you're supposed to have 6 Pokemon, but anyway, these are the Pokemon I found. And at this point in time, you're here at a professional conference, so you might wonder, geez, is this guy going to talk about Pokemon the entire time? The answer is yes. But there's also an interesting lesson here, because what happened next, can you see when the blog post was written? No. But you can see when Reddit picked it up. So apparently there's a very active Reddit community for Pokemon fans. I would not have guessed it. And they found my blog post and they were discussing it on Reddit, which is this international forum. And I looked at the forum, and it turns out that the Pokemon fans did not agree with my modeling methods whatsoever. But they did agree that the output of the model made sense. They did say, hey, yeah, the Pokemon he found, those are actually some of the pretty good ones. Even though the way that you simulated this was completely not how the world is supposed to work. But yeah, the conclusions are, they are actually kind of sensible. So you have to imagine this happened like maybe 6, maybe 5 years ago. And this was something that I thought really mattered, because Pokemon is a relatively complicated, domain-heavy video game. And I was able to make a better decision without having to learn Pokemon whatsoever. I still don't know all the Pokemon, to be honest. My girlfriend plays the game more than I do. And the only thing I did here was trying to learn from data, and then using a couple of algorithms and some math tricks. But that was the idea. And this, to me, was evidence that this whole data science thing was fundamentally different than business intelligence. I'm not going to give you insights. I'm going to help you make better decisions. And it's that part that seemed very interesting to me. So on one end of the spectrum, we've got the BI stuff, and the other end of the spectrum is the ML stuff. And I figured 5 years ago, the only thing I got to do to compete with all these BI and these other consultancies, the only thing I got to do is sort of tell them this story of, hey, this is what we used to do, and this is what we're going to do. And that was sort of the transition that made me sort of think, hey, I should invest in this career path, because I do think that there's a lot of good stuff to be done here. So the main takeaway was, we can quickly bootstrap solutions given data, even if you lack domain knowledge. And if you're a consultant in IT, you don't have any domain knowledge. You can go to a supermarket, know nothing about a supermarket, but if you can do stuff with data, then maybe you can still help them make better decisions. So that's super interesting. That means that you have a solid background. And this video game example seemed like a nice analogy for something that I might do in business. It's a really silly example, because again, I have to stress this is like a Japanese movie or something, right? This is a really silly example. But it is an example that made a lot of business people go, huh, okay, I get what this data is about. This is different than BI. So the future was looking bright. Like AI was going to replace BI, and AI was going to be the thing. That also meant that the old ways of doing things was going to go away. So data going in, we have some rules, and then we have some labels and decisions. That was going to sort of go away a bit. And instead what we were going to do is we're going to say, hey, let's put some labels and data into a model, and then have rules come out on the other side. And that kind of felt like the path we were supposed to take. This was 5 years ago. And I have to say, my opinion on this has fundamentally shifted. I actually think it's less of a good idea now. And what I hope to do today is explain to you why it's okay to be a little bit skeptical. I think the future looked so bright 5 years ago that we kind of got blinded by it. And we may be at risk of solving the wrong problem, but we're also at risk of solving it the wrong way. And what I hope to explain with a few of these examples is that we should be very cautious. At the end, I will also give a remedy and a glimpse of recent work that I'll be working on, hopefully to inspire some conversation afterwards. So what I'll tell you is a tale about a textbook example that's going bad. I'll give you an example of how most classification algorithms will fail out of the get-go. I'll tell you a story about hormones and pregnancy, one about elephants. I will discuss something about the current solutions out there that aren't really helping, and I will discuss a little bit what the consequences are for chatbots. So I hope we're kind of excited about that. So how do we do ML? Well, typically what we do, right, is we get our data, we get our labels, and we put that into some machine learning thing, and out come the rules, and we can, I don't know, it's either in a jar or in a Python pickle. We put that in the server somewhere, and then let's call this in production. And the idea is that then new data comes in, and we can make a prediction, and then hopefully profit happens, right? That's kind of the idea. We make a prediction about something, hopefully that allows us to make a better decision as well, and this will lead to more money, happier customers, whatever. But this is kind of the flow. You start with data, and then you have this machine learning thing. And again, that's this, right? So this is the data and labels going into the model, and out come the rules. The interesting thing, if you look at the books and also lots of conference talks, is that most of the attention go into either which algorithm are we going to choose and how are we going to go about deciding which algorithm to use, and how do we get that algorithm then into production. That's where most of the attention is spent. And a machine learning algorithm usually consists of a couple of parts, right? We have this pre-processing part, we've got this algorithm part, and usually both of these parts have many different settings that you can try. So people like to call them hyperparameters, but there's all these different settings that people sort of go for. Scikit-learn is an example of an API that really adheres to this as well. It's quite a good library. And you know, this is actually computationally quite expensive, because let's say that you've got some settings for this pre-processing part and some settings for this algorithm. I mean, if there's 2 settings for this guy and like 5 settings for this one, then you've got 10 settings you got to figure out. And if there's another setting you want to figure out, you know, this thing kind of starts growing exponentially. So if we're going to try out all of these different settings, we have to be aware it's going to be very, very costly. But we don't mind doing that because we want to have the best algorithm, right? That's the thing we're trying to focus on. The best algorithm is the thing that's going to give us the most profit. So not only are we going to loop over all of these settings, but we're also going to cross-validate that. And I'm assuming this crowd has heard of this train-test split before, right? So there's this data set that you learn from and there's this data set that you test on. And typically what you would do is you would say, let's not have one train and one test set. Let's instead say, hey, we're going to take our entire data set, split it up into different segments. And then the idea is, first the first segment is going to be the test set, then the second segment is going to be the test set, then the third and the fourth. And then you have a couple of these test sets. And what you can then do is for each and every one of these test sets, you also have a train set, so you can train a model, and then you can get some scores that come out of this test set. And then you can average that and summarize that, and then hopefully for every single setting that you make, you kind of have this number that says how well that setting for that model is doing on your data set for your task. So you get this test score performance thing that comes out. And you do this for all sorts of different settings. So I hope that we appreciate there's a whole lot of compute power going on here. So it better be worth it what we're doing. If this is something we shouldn't be doing, it would be a bad thing, because a lot of resources are being spent on this. I hope that's clear. Because for every single cross-validation, for every single setting, we got to train a model. And especially if we have big data sets, this thing's going to get expensive quick, right? I hope that a lot of engineering effort actually goes into scaling this on massive machine clusters. So it better be worth it that we're doing all of this. Because the compute time, again, is proportional to the settings and the number of cross-validations that we're doing. But at the end, what you typically get is you get sort of this grid search result. And I'll do a bit of live coding to sort of show you what this looks like. But typically what you then have is this long list of, hey, I got all these settings, and I got all these numbers that I maybe care for. Some people care about accuracy, other people care about precision. And typically what you do is you report on the mean test statistic. And there's all these settings that you sort of just check. And you can determine yourself which metric is appropriate. Maybe you like precision that says, hey, if I say that you're pregnant, how sure am I that you're actually pregnant? You can also say something about recall. I want to have all the pregnant people, right? So those are 2 different metrics. You can pick a metric that fits your business needs very well. But in general, this is the way that you do things, and this is what people typically do. The goal here is that we want to prevent our model from overfitting on a data set. And I think that this idea has merit to it, because we want our models to generalize. By splitting up into many test sets, we hope to get a robust single number that tells us how well our predictions are. Because we don't want to put something in production that's going to be making wrong decisions. The whole reason why we're doing this grid search and cross-validation, all of that, is because we don't want to have something in production that will make wrong decisions on our behalf. But then, if that's the case, I got to ask the question, is this grid search enough? Is this grid search really going to guarantee that no bad things will happen? Because it really seems to be the industry focus at this point. And the reason why I think it's important to think about that is I meet a lot of people who basically say this, like I looped over a bunch of settings and now I solved disease diagnosis. By looping over all these settings, I have a number that says my machine learning model is great. So I think it's good to then show you what a potential failure scenario might look like. So what I'm going to do now is I'm going to open up this Jupyter notebook. You will see some code. I'm going to run you through what's in there, and then we're going to have a bit of a discussion, and hopefully we can judge whether or not we like what we see. I believe that's in my... I had that thing open just now, didn't I? Sorry about that. Yes, let's restart this guy. There we go. So what I've got here is a notebook called What Could Go Wrong. So hopefully there's something ominous about that we're seeing. And what I'm doing here in the beginning is I'm just importing a whole bunch of data sets. For those of you that are a little bit less familiar with Python, this is an interactive playground. It's easy to make plots in. And if you're a data scientist, this is typically a work environment that you're used to. And what I'm doing here is I'm importing a data set, which is the Boston housing data set. It's a data set that's actually super frequently used in books to explain how machine learning works. It's a data set that contains information about houses, and then you have to predict the house price. So square meters, how big is your garden, how far away from schools are you, these sorts of things. And what you typically then do is you say, hey, there's these things I want to predict. That's something we like to call Y. It's from the math books. And there's these things that we're allowed to use to make this prediction. That thing is called X. And like I showed you before, there's usually like a pipeline. And in Python, I think scikit-learn is the most elegant way to declare that. So I can say, hey, I'm going to do some scaling, the data going in. I'm going to make sure that it's kind of normalized before I give that to the algorithm. So I say, hey, here's a scaling step, and then there's this ridge regression step that I'll be doing. And what you can then do is you can say, hey, this pipeline, what are all the settings that I can tweak? Well, so there's like a tolerance for the model. There's like, hey, do I scale with the mean or scale with the standard deviation? And there's all sorts of things that we can try. And what scikit-learn also offers us is a very convenient API to say, hey, these are the settings I just want to change, and could you maybe spread that out over multiple cores and just run that for me, please? And that's what happens here. So again, I have my data set, my X and my Y. I've got my pipeline of steps, so I'm going to normalize first and then do the prediction. And I'm saying, hey, let's do 5 cross-validations. So split the data set into 5 bits. First, that's the test set, then this, then this, then this, and this. And there's this grid. So we can say, hey, I want you to scale with the mean, true, false. I want you to scale with standard deviation, true, false. And there's this alpha parameter in the model. I want you to try out all of those. And mean squared error is the thing that I mainly care for. So let's just say the mean squared error, that's something I want you to optimize for. That's also something I can give it. What's going to happen is it's going to loop over all of these different settings, loop over all these different cross-validations, figure out which of those configurations has the best mean squared error, and then this is going to retrain on the entire data set, and then I have the best model. And this is what people typically do, and a lot of data scientists, they heavily focus on this, because this is the methodology that research papers like to adhere to. You really have to cross-validate your data quite well. So, I have to run the whole thing then, because I just restarted this. Yep. So this, you call fit, and then this model is fit. And what you can then also do is there's this property in a grid search model called CV results, and this will give you like a nice little table of all the grid search results. And what we can do is I'm just taking the top 5 rows and I'm sorting. And one thing that's kind of interesting, I think, is always looking at this is sort of say, hey, which parameters seem to be doing well? And it seems that, we can have all these, the scaling doesn't really matter much. The main thing that seems to work is this parameter alpha. And that's something you can read from this grid search, and you can zoom in on this and focus on this, and then you can convince yourself that what you're doing is pretty good. And if you're a pretty good data scientist, what you then also do is you also make plots like this. So you have your x-axis, you've got your y-axis, and then what you sort of do is you check if there's like a little correlation here. This is the predicted price. This is the actual price. We see something interesting, like the model actually makes a very stupid decision here. It predicts a negative price, so there's something still wrong with the model, but it's a reasonably straight line, so we can convince ourselves again that we're doing kind of the good thing. And this is the flow a lot of data scientists have. They sort of say, look, we're doing the good thing, it's optimizing, the number we care about is sort of high or low, and that's what we like. What most data scientists don't do, and I'm sad to say what most books on the matter also don't do, is just check the column names that we're using to make this prediction. Because to me it feels, if I'm going to make a prediction, and it's my responsibility what data goes out of the model, then maybe the data goes into the model is also something I got to be concerned about. So let's just have a peek at which columns are in here and that we're sort of using. I'd like to zoom in on this one. So there's this weird formula where there's a parameter going in, where one of the parameters is the proportion of blacks by town. Now we have to remember this data set's from the 70s, right? So I'm having a really hard time coming up with a use case for this particular data set where the model's not like data laundering pre-existing bias. And here's the tricky thing. If you're a data scientist and you're focusing on this, you're focusing on, oh, I've got the best summary statistics, right? And you're taught that way. You're taught to really think about it in a quantitative way. This is one of those things that you're just gonna miss. And you're missing a big one, because this is like a pretty good recipe for a racist algorithm if you think about it. And there's some other stuff in here that I also don't really like lower status of the population. Not too sure if I like that. Now I gotta say, one thing I do like about having these two variables in there is I can also apply some fairness type algorithms to sort of compensate for this, right? If I didn't know these two columns, then there would be no way for me to compensate for them either. But to just throw everything into a model, call fit predict, and then hoping everything's great feels extremely naive. And it's actually kind of embarrassing how often this data set is used in books, even though, this property is in here. Now, it deserves to be mentioned that recently, I've been talking about that one thing for a while, but other people have also been talking about it, and this data set is now going away from scikit-learn. They're removing it. They're looking for a new data set to replace this. So the open source committers are actually aware of this, and they're looking to change this. But this is one of those things where, oops. Machine learning is great, but maybe we shouldn't listen to this guy. So fairness is one obvious use case where a lot of machine learning fails, and it's a fair thing to look at. But there's also other areas where I think it might be harmful. So I'll show you another example, which is my favorite example of artificial stupidity. And this one concerns classification algorithms. And I must stress, I think I know of no algorithms that don't have this problem. Typically, you might say, hey, we have some sort of algorithm that outputs a prediction. Predict proba, if you're used to scikit-learn. And the prediction is, usually between 0 and 1. So if there's two classes, if one class is A, the other one is B, we can say something like, okay, it's class A if the probability is lower than 50%, and it's going to be the other class if it's higher than 50%. It's something that you can do to the classification algorithms. You can convert a probability to a class, and you typically do it this way. And if you're a little bit more concerned, what you can do is you can say, hey, you know what? I'm going to maybe move that threshold a bit. I really care about getting my class B right, so I'm going to be more strict. Only when the algorithm outputs a super high percentage, then and only then am I going to care about it. What you can also do, and unfortunately most people don't do this, but I think it's a really cool trick, is you can also say, how about I have this won't predict thing. And the idea here is that you say, hey, only if I'm super sure that it's class A or if I'm super sure that it's class B, then I'm going to automate the decision, and I'm going to raise a won't predict flag in other cases. Which is a reasonable thing to do. You don't want to automate something that you're reasonably unsure about. So having that boundary in the middle to sort of say, hey, let's not automate this thing, seems like a really, really reasonable thing. It'll look like this if it's on a one-dimensional thing, right? So probability of A goes down, B goes up, stuff in the middle, don't touch it. But let's see where this idea goes horribly wrong. So I've got this example data set, and it's a fake data set. It doesn't represent anything besides blue, green, and red dots. But let's train a classification algorithm on it. So this is the actual data set. What I'm now going to do is I'm going to train a k-nearest neighbor algorithm. It's just my favorite algorithm. And then we're going to see how the decisions are being split across the 3 groups. So again, this is the output of the classification model. You can actually see there's clear boundaries now, right? There's this moment where, hey, you're class A, and then you're class B. And what I can now do is I can say, let's remove all the points where there's uncertainty. Right, so the stuff that's in the middle, that's the areas where we're uncertain about. So hopefully these points, those are points that we can actually say confidently, hey, yeah, those are actually belonging to the red dots, the blue dots, or the green dots. And again, not a bad idea, but something's going to go wrong. This is the starting point. What I'm now going to do is I'm going to draw all of these points black, and the background is going to represent the color that the classification algorithm, the classification algorithm is going to be making. So where it's more light, you see that's where the uncertainty limit strikes, so we're not going to make any predictions there. And then we have the green, the red, and the blue parts. So this is what the decision the algorithm is making. But to show how incredibly stupid this is, let's just zoom out a bit. Notice that you can be like so far away you don't hear the bell curve ringing anymore, right? So you can be like way out there. The algorithm is going to say, oop, yep, definitely red. Even though it's nowhere near any of the data points that we've seen before. So to me, that feels super risky to make a decision about that. And the model's not going to help you here. Logistic regression, random forest, also deep learning, they all get fooled this way. And I kind of get why, because an algorithm always has to say it's either this class or that one or that one. And distance-wise, yeah, I guess this point over here would be much closer to the red points than to the blue ones. But I would prefer if the algorithm was also able to say, look, I'm just super uncertain here. And I also hope it's clear that this whole predict-proba thing is not the same as certainty. It just simply isn't. It's a proxy for it, but it simply doesn't mean the same thing. It's an approximation of a probability. It's not the same thing as certainty. So the model's not going to save you, and neither is this grid search. This grid search is just going to tell you, on the data that we actually have, this is how well the model's performing. Which again should be regarded as a proxy. It's not ground truth. It doesn't tell you anything about what's going to happen in production. But it is something we're overfitting on. And grid search is not going to help you, and I also don't think this consultancy guy is going to help you. But I do hope that we recognize maybe this story where, the guy has a PhD and he's wearing a suit, so if you're a senior person, you're going to go, man, I got to trust this. There's a chart and everything. But I cannot blame, I call him Nimrod. I cannot blame Nimrod here, because Nimrod was probably taught as a PhD to really focus on his benchmarks. Because if you're writing an article or a paper, that's the thing you got to prove your algorithm against. So remember 5 years ago that people said machine learning was going to replace business rules? I think these people were wrong. I think that ML is super useful to be used inside of business rules. Because how cool is this? How about you say, look, I've got my X, it's going to go in. If we say that X is maybe an outlier, it's too far away from data points that we've seen before, then we just introduce a fallback scenario. And we do the same thing for when the model's uncertain about a class. Then and only then we'll take an action. To me, this feels like really sane system design. And detecting outliers, it's not necessarily a solved problem, but we do have algorithms for it. So it's not like we can't do that as an extra step in our pipeline, but we're taught to not do this. We're taught to really just focus on the machine learning grid search. And I hope that these 2 examples kind of paint a clear picture of why that might be dangerous. So algorithms, I think, are designed for interpolation and not extrapolation. It's really easy to calculate the middle number. The mean is accurate, but the stuff that's on the sides of the distribution, that's usually quite hard to estimate. And I think that constraining the algorithm by denying certain predictions seems like a really nice idea to have in production. Having a fallback scenario is probably the first thing you should think about before you start worrying about the algorithm. The algorithm is usually just a small cog in your system anyway. It's all the stuff around the algorithm that you've got to concern yourself with. So I'm going to tell you a story that I heard at PyData Poland. And it was actually kind of badass. It was a nurse in a hospital who did this. So when you're pregnant, I've been told, I'm not an expert on this, but when you're pregnant, while you're delivering the baby, what they sometimes do is they give you this hormone that helps with the delivery. Now, the amount of hormone that they give you, there's been lots of research on that, but I believe it was done in the US in the 70s on women between 19 and 21 or something like that. So then, if you train an algorithm on it, you're going to get something like this, and you might, plausibly wonder, if you have a little bit of domain knowledge, that if you're older, then maybe the way that your body reacts to hormones is different, right? So maybe we shouldn't pretend that this is a good idea, even though an algorithm says so. And I think in general, especially in the medical field, it's pretty proven right now that most of the tests that have happened on men, and if they've happened on women, it's really dated data, so it's an area of research to get that data in the first place. But it's super naive to assume that the grid search has saved you here. It's not enough, we need more. And accuracy in this case, I think artificial accuracy is going to become a term this year. And I think the problem here is that there's this ivory tower where there's this person saying, hey, I solved the problem by looping over a bunch of settings, and that there's sort of this distance between the actual hospital. I think the person who is doing the stuff in the notebook is not the same person who's on the floor as a doctor trying to help patients. And it's that distance, I think, that's part of the problem as well. I cannot completely blame Nimrod for only being in an ivory tower, but I do think it's a good idea if he sometimes goes to the hospital. So this year I started wondering if constraining is enough. It seems like a super good idea, but it doesn't completely fix the ivory tower problem. So I think it's time for another story. So imagine that you're a ranger and it's your job to protect elephants from poaching, right? So these elephants are precious. I know I'm an animal fan. Elephants are cool. But the thing with elephants is they're not like dogs. They don't like it if you stick a microphone or a sensor on them. And if you don't disagree with an elephant, right? You're going to get killed. So imagine that you're a ranger and it's your job to protect these elephants from poaching. Then a large part of the protecting of the elephant herds is understanding the movement patterns in the national park. And again, the national parks, especially in Africa, they can be the size of the Netherlands, right? These are huge national parks. So you can't have a camera or eyes and ears everywhere. So what you can do then instead is you can have this mic array of all these different microphones across the entire park. And then what you do is you just have these microphones try and detect elephants. That's the idea. So if there's an elephant sound, detect that and then tell the rangers about it. But the cool thing here is all this audio is going to generate so much audio, we cannot really listen to this by hand. So instead what we do is we go to a PhD researcher who happens to be an expert on audio analysis. We give him some elephant noises, and then he trains an algorithm, and it says, oh, it's super accurate, we can totally push this to production now. So the rangers get excited, they invest a ton of money, and then all of these microphones in the field can detect elephants. And then when they're trying it out, they kind of figure that whenever they hear an elephant and they go there, the elephant's gone. So it's not really working for some reason. And the thing that went wrong here is that what the PhD person did, the PhD person just said, hey, I've got this algorithm, let's just apply it. What the PhD person didn't do was actually listen to the audio clip, because then you would have heard gunshots. And if you would have listened to the gunshots, you would have gone, oh, that's probably more interesting to detect. And this is one of those moments where, hey, we have an actual problem, we translate that to, let's say, an analytical problem, we optimize the analytical problem, which is great, but then the translation error back to the original problem is not going to be compensated by the optimization you did on this side. And again, this is one of those stories, but I've been a consultant for a couple of years, and I've seen this happen a whole bunch. And I think a lot of it is this. So you have an actual problem, and you want the production results to be good. You translate that to a data problem, and then you have these grid search results. And then the grid search is the thing that people optimize for, but the thing that really matters is this. And it's great if you can sort of squeeze 1% out of your grid search results. That's great, right? Let's do that. But if there's a 10% translation error happening anyway, then spinning up your giant compute cluster to optimize whatever's happening here feels like a farce. It's probably a better idea to make sure you're not in the ivory tower in the first place and make sure you understand the problem really well before you make this translation step anyway. And we do have a tendency in data science, I think, to say, hey, if it doesn't fit predict, it's not data science. So we tend to sort of see everything as nails because we've got this hammer. And maybe all we need is a for loop, right? McKinsey wrote this article about this analytics translator role, that's going to be something that organizations need. And I get what they're trying to do there, but I think they've really done the wording wrong there. I get that analytics is a buzzword, but we don't need people to translate the analytics to the problem. We We need people to translate the problem to the analytics instead. That's the thing we should be going for, and I think that's also a more rare skill set. Because again, you've got the domain knowledge people, you've got the data expert people, and it's probably a better idea to give like a little bit of tech to the domain guy than to assume that the quantitative expert PhD guy is going to understand all of your domain knowledge in the short term. I think we are maybe overfitting on the qualifications of artificial intelligence here. Another part of the problem is that people don't think ahead. If you make a prediction that in turn is going to cause a decision, that in turn is going to change the world, that is going to lead to more profit, right? That's what we sort of assume. We have a prediction. We can then anticipate the prediction better and make a better decision. I mean, that's great. But we should not assume that the world doesn't change and that then the predictions are going to remain as accurate. If you change the world, that also means that your training data set that you're using now is no longer relevant because the world has changed. What you're learning on is a different version of the world than what you've caused. And if you're not thinking about this feedback mechanism when you're deploying, there's this thing called drift in machine learning. If you're giving a different recommendation, people are going to click on different things, and you want to prevent this self-fulfilling prophecy. Not thinking about this ahead of time is going to lead to a lot of pain. If you deploy machine learning to production and the accuracy keeps getting up, be really, really worried. Because you're hitting the self-fulfilling prophecy, I think. So I hope at this point some of you sort of think, all right, this is actually a little bit cause of concern. These are valid points. But we should also talk about remedies and solutions, I think. It's okay to sort of point the finger and saying stuff is wrong, but it's also important to sort of say, hey, how can we fix some of these things? But there are lots of solutions out there. I didn't make the full diagram of all the vendors out there, but like, when people talk data science, they typically name some of these things. So there's Keras and Scikit-learn and PyTorch. Some of the stuff you see here is from the cloud providers. Some of the stuff you see here is open source. But when people think, hey, let's do machine learning, let's do production and all these things, then these are sort of the names and the tools that you might see. And to me, they sound really, really familiar. Pandas and PyTorch, could have been a Pikachu or a Ditto or a Snorlax or something like that. So we got to catch them all, right? We got to have all the tools in there. At some point in my career, I noticed, geez, there are really a whole lot of tools, and they keep introducing new ones. This is actually kind of becoming a joke. It is literally like Pokemon Blue came out, and there's like 6 new Pokemons. So at some point, I made a joke about it, and it became a meme again. You might have seen this picture on LinkedIn. This was at a tech conference at PyData Berlin, where I said, look, this was actually my LinkedIn profile as well. I do R, Python, JavaScript, Shiny, dplyr, Ditto, Purr, Canvas, Spark, Sock, and I basically interchange the open source projects with the Pokemon names. And then I typically ask recruiters to point out which of these are Pokemon before they attempt to hire me. If you now Google meme recruiter Pokemon, this thing is trending. I've been contacted by the biggest tech recruitment conference in the United States if I want to be a keynote speaker. Supposedly all the recruiters now know who I am, which is the exact opposite of what I was trying to achieve with that thing. Back to this, but I do think that there's this sense of, hey, we got to collect all the tools because all these tools solve a different problem. But what do these tools actually do? Because if I think about all the problems that I've just alluded to, right, do these tools actually solve all the problems that I've just shown you? Because some of these problems occur because we're automating something and optimizing religiously for one single number. So, and maybe what I can do is I can plot all these tools sort of on an axis and sort of wonder where they stand. And as I was looking at this, I kind of figured, hey, this is this sort of machine learning production cycle, kind of, where on one side of the spectrum you've sort of got total production, so that's cloud provider tools and that sort of thing. And in the middle you kind of get like analysis, exploration, data science, algorithm stuff, right? So you got production on that end. And then I started noticing there's kind of a gap there at the beginning. Because all of these tools, they solve stuff that you can automate. You want to do a grid search? Well, it's a for loop. Can we distribute that? Yes. OK. GIF wrapping around it, it's a product. We can sell it to people. But understanding the problem in your business, that's super hard to automate unless you have a business that scales very well and is really, really common. A recommender for Netflix is fundamentally different than a recommender for a grocery store. It's really hard to come up with good recommendation software that works for everyone as well. And if I think about the original problems that we have, like, hey, with this translation thing that's kind of going bad, I don't see many tools that really try to address that. And maybe, if you want to prevent artificial stupidity, maybe we shouldn't worry too much about the stuff that's over here, and maybe we should worry a bit more about the stuff that's missing over here. So I also try to make some meaningful contributions here and there. So if you're interested in anything that has to do with fairness or like prevention mechanisms for scikit-learn and that sort of thing, come talk to me. I've started this project together with a couple of collaborators called scikit-lego. I'm really interested to hear if you folks need more features. But it's a mere remedy. We need something there, something on that data set quality part. That's something that's currently totally missing. And it's not just data sets, but there's loads of stuff that's missing there. I will say there's this one tool that is actually super cool, and I have to, like, they're buddies of mine who started that. They're the Spacey people. There's this labeling software called Prodigy. It's quite good. Like, it really is quite good, because the idea behind Prodigy is, let's empower the data scientists to label data themselves, and in doing so, they're already a little bit less in the ivory tower. And it also makes this labeling sort of a shared responsibility. It's no longer the data scientist going, oh, I only do algorithms, but now everyone in the organization has to label, and you get really good discussions about what makes a good label, etc. But it's not enough, because I also think stuff like ethics, and how will the world react, and governance, and data quality in general, that it's got to be kind of in there. But if I were starting a new data science project, sure, there's production stuff, but let's think about stuff we can do there. I think if you're a data scientist and you want to take yourself serious in this day and age, you want to call yourself a senior or whatever, that's the thing you got to worry about. Because the moment that your data quality is off, you can have the best algorithm, right? You can have an algorithm that totally kicks XGBoost's ass, right? That's totally cool. But if your labels are wrong and if your data quality is wrong in general, it's all going to come crumbling down in your application layer. All this stuff builds on top of each other. If your analysis is wrong, production's going to fail. But if your data quality is off, everything will fall like a house of cards. So that brings me to where I am now. I've been doing consultancy for the last 6 years, and after a while, you should really do something else, I think. So I joined this company called Raza. And what I now do is I try to focus more on natural language processing. I think it's a very interesting field. I think language in general is the most awesome invention we as a human race have ever made. It turns out it's really, really tricky though. And it's also kind of this thing where my dad became a skeptic. So my dad actually came up to me during Christmas saying, like, you're going to continue your crusade against hype at a company that specializes in chatbots? I would like to explain why the answer to that question is yes. There's this company called Hugging Face, and they make cool stuff. I want to say that first and foremost. And they have this blog post called How to Build a State-of-the-Art Conversational AI with Transfer Learning. And again, what they're doing here is actually genuinely quite impressive. But I'll just show you what a typical conversation with a typical deep learning algorithm can be like. So I say, hi there. I get the reply, hey, how are you doing? I'm doing well, I just fed the cats. And then the reply is, oh, that is great. I just got done dressing up out to go clubbing. Okay. To where? To a bar near my apartment. Then I ask, what kind of music? Rap, country, and rap. Okay. Come again. I hope to get a few more procedures done. Like at the dance floor. I hope to be happy with myself. Why go out then? I'm saving money for surgery. A few things I want to point out. This is really hard stuff they're trying to do here, right? So they're saying, like, hey, like, these are like proper sentences. That already on its own is actually not bad. But this is not a conversation. And especially in a chatbot setting, this is not ready for prime time, right? You can have the best article about this. You can be #1 on the NeurIPS conference, but I mean, this is not going to go to production. So what might be the best way of solving this? Well, we saw earlier that one way of sort of preventing this stupidity thing from happening, maybe, right, is to constrain it. Maybe the problem here is that the algorithm has a bit too much freedom. The bot can probably talk about whatever it feels like. And as an algorithm designer, I didn't really have a button to say, hey, you're only allowed to talk about these certain things, right? This bot has a lot of freedom. And there's a reason why you put like a fence near a ravine. You just don't want people to sort of go over it. So how do we do that over at Raza? Well, we kind of do this. We basically say there's this notion of a story, right? So so when someone wants to be greeted, then we sort of say, oh, hello, and then we ask for features. And this is what we call an intent. And there's only a limited set of those, and you have to provide them as a user. So like explicitly, at the moment, you can only have a chatbot that does only what you tell it to. The only intents that it's able to detect are the ones that you give it. It will not do anything with anything else that is being uttered. So what we then do is we say, okay, for every single intent, we just need you to provide us with lots and lots of examples, and then we'll just have a classification algorithm say, oh, okay, this is the intent right now. We then check if that intent matches a predefined story, because, you know, certain questions should follow up on each other questions don't. And only when there's a proper match, then we say, okay, this is the conversation, this should be the reply. So that allows me to build any sorts of mechanisms that say, oh, that's unclear, could you maybe check? I want to verify, pardon, all of those sorts of things. And you can say in this case, yes, I'm definitely constraining the algorithm, but I would argue if for production purposes, this is a good thing. But you know what's also a good thing? This is also how you design the chatbot in general. So as a programmer, you have to actually have these examples put in yourself. This is a markdown file. That's the basis of how we make chatbots. And you can customize them with your own algorithms, and that's fine, but you are definitely sort of touching this. There's also another reason why I think chatbots are hard. And if you're in the chatbot community, you already know this example, and I think it's just funny. So this was, I think, like a secret photo taken at the first demo of the PayPal chatbot. So someone says, hi, I'm PayPal's virtual agent. To get started, simply ask me a question. I'm still learning, so if I can't help you, I'll direct you to additional resources. This guy called Brady says, I got scammed, and PayPal says, great. And I mean, and what happened here, you know, we can think about it. What happened here? Well, there can be two things, but probably one of the things that's at the core of all of this is that the person who designed this chatbot did not think that maybe someone would say something about being scammed. It's well possible that you have lots of intents here, but not all the ones that people are going to be asking for, right? Well, that's well possible. So there's two ways of thinking about that. One way to think about this is we should have something of an outlier detection system here, right? So something that what we showed before, like, hey, that's out of scope. Yep. Or what we should do is we should think about this angle. So what Raza currently does as an open source product is we connect with TensorFlow and the messengers and all these different databases. That's stuff that we can handle for you. But something that we've been working on recently is this thing called Raza X. And what is that thing? Well, it's, you know, it also does CI/CD, but it also does labeling. And it does live labeling too. So this is a screenshot of the user interface. You can have all sorts of conversations, and you can label where they went wrong. So you as a data scientist, you can just log into this thing. You can look at a conversation where it went wrong, relabel it, retrain the algorithm. And in fact, I think this is the best way to go about it, because that's the way that you're going to fix this distance. As a data scientist, you have to maybe listen to these people. OK, so I'll be closing up. Stop sign guy. Final thoughts. So I hope that we're now a little bit more skeptic about these accuracy numbers. If we trust them too much, I mean, artificial stupidity is just going to happen. And I also hope that I've been able to convince you that maybe the focus should be moving away from the algorithm and maybe more towards the data and the use case. If the predictions going out of our systems are our responsibility, then so is the data going in. It's part of it. You're unprofessional if you consider this is not true. I do think we should start considering fairness a bit more. It's getting concerning. And I also think that we should be doing stuff with outliers. Now, I should say I'm also in the research team of Raza, so we are thinking about this, but outlier detection in chatbot settings is hard, but this is definitely an area of research for us. But maybe, just maybe we should appreciate the quality more than the quantity. Has there ever been an end user come up to you and complain about a low mean squared error or a bad ROC curve? Or have you ever heard anyone say this website sucks because they're not using Vue? Because usually what they say is this website doesn't do what I expect, and that's the problem. It's not that you're not using the latest tech, it's just the website is not doing what you want it to. So maybe if we're building dialogue systems, maybe I shouldn't predict what to say. Maybe we should learn how to listen. I think that's an interesting vantage point. So I'm building this chatbot for Pokemon, and the only thing it does is ask users, what would you like me to be able to do? Let me know if you're interested about that. Thanks for listening.
We'll be taking questions. Thank you, Vincent. I can ask the first question, since you sort of, is there a difference between the kind of chatbot that you talked with and what Raza does. Is there this language of open domain chatbots and closed or?
So I got to be kind of careful here because this is like my third week at Raza, so I'm not super aware of everything that's in there. But what I will say, there is this research effort that tries to do end-to-end chatbots. So it's just a deep neural network that you're trying to talk to. That's not the current flow that we adhere to at Raza. What we sort of say is, you know, it's probably a better idea to just constrain it a little bit and say, look, these are the things that we're classifying for. And you can have something like BERT detect the intent, like that's stuff that we do allow. But we do like this notion of having stories because it constrains the algorithm a bit, but it's also nicer for domain people to get a grip of what's sort of happening. It's a nice metaphor for how a conversation should go, and you want some sort of structure there. Just throwing that into a black box seems like it's not going to be ready for prime time anytime soon.
Absolutely agree. Any questions?
Hi. Yeah, you talked a lot about basically crap in is crap out, which makes a lot of sense. But I know there are some places that are actually doing research into data drift to make sure that you know when you need to retrain your model. Do you have any insights on good projects that are going on right now, which we should pay attention to?
So over at Scikit Lego, we are trying to figure this out as well. I've heard that there's this project called Scikit Multiflow that might have stuff in it. I've not looked at the project. It's just some dude at a meetup told me about it. So I do know that I think SciPy has support for some of this stuff if you have one-dimensional drift. So a one-dimensional number, if that's changing too much as a distribution, they have support for some of those metrics. The hard part is, what if you have instead a giant data set and continuous variables, discrete variables, and times, and all sorts of things like that. And I've not seen anything that makes me sort of go, that's the obvious solution. Well,
I might know someone you might want to talk to.
Oh, sure. Like, I'm always interested in implementing other people's algorithms. That's always great.
Questions?
I'll also be around for like the AMA tomorrow, and if you have questions about anything, just drop by.
First of all, thank you for pointing out how the UXers should be closer to the data scientist. I've been preaching that at my consultancy company, so thank you. So question is, how would you aggregate a company's data from different sources, being a consultancy company, in a secure way, and more convince the tech leads or IT directors to let you do it? Because they're so paranoid about, well, not paranoid, but afraid of digital breaches, you know?
Right. So being afraid of digital breach, I think that's normal, right? That's probably a sign of sanity, especially if you're in a regulated industry like healthcare or whatnot. I should say most of my clients have not had this issue, but one thing that you might want to think about is your average data scientist is not the biggest security expert, typically. And typically the person who's really good at security, they're not going to be in a data science team. These engineers are typically someplace else. But what you can maybe think about is saying, how about we have this, I don't know, people sometimes like to call it the master table, but one thing that you can sort of say is the engineers, they consolidate this one data set that's encrypted and sort of privatized, et cetera, and that's the thing the data scientists can play with. The idea there being is that you sort of scope down where the breach might happen to this one single data set. And then sort of you can tell the security people, hey, there's only one table you got to worry about, and that might be the nicest way to communicate. Again, like, security practices are something you have to take serious, and it's not really my domain expertise, but this idea of let's just have one table be consolidated by the engineers, not just for security practices, but also for data quality practices, I've seen that work relatively well. So that might be a thing to push for.
Okay, I think we're out of time. Thank you very much, Vincent. Please welcome me, help me welcome and thank Vincent for the presentation.
No worries.